Sharing my screen now. Can you see my screen?
Yes, sir.
Okay, thank you. Okay, so let me recall what we did in the last class. So in the last class, we saw the importance of unitarily equivalence or unitarily similarity transformation under the or over the usual or standard similarity transformation. So there are many advantages of having a unitary matrix. Uh, and if we perform similarity transformation using unitary matrices, then we achieve many things. Especially numerically, there are many advantages of having unitary matrices in the computation. Then we saw that not we know that not every matrix is diagonalizable, but there is a way to upper triangularize it, or we can say that if we have a complex matrix of size n cross n, then this matrix is similar to or unitarily similar to an upper triangular matrix. And this is called Schur's lemma. There are many applications of Schur's lemma. We will see in today's lecture. Some of them we will see in today's lecture. But what it says, let me recall what it says that Schur's lemma. So there are two versions of Schur's lemma. So the first one is the complex one for the complex matrices. So what it says, let me state that again. It says that if we have a complex matrix n, complex matrix A of size n cross n, then there exists a unitary matrix U, and suppose that further, if suppose that lambda 1 to lambda n, these are the eigenvalues of A, which are in some order, okay, which are some prescribed order. Now this Schur's lemma says that there exists a unitary matrix U of size n cross n, this is unitary, such that U star AU is upper triangular where the triangular matrix has diagonal entries in this order. Okay, so this is for uh, this is n cross n. This is for a complex n cross n matrix. Now, why I am mentioning complex n cross n matrix? Because if it is a real matrix, of course, when you have a matrix A with real entries, that means all the entries are real, then still this is a matrix. You can see, look at this matrix over C also, and then you can find a unitary matrix as that U star AU is upper triangular. But the thing is that, or the question is, can we find a real orthogonal matrix instead of unitary? Can we find a real orthogonal matrix Q such that Q star AQ or Q transpose AQ is upper triangular? But then this is not in general true, because we know that if this is true, then then every real matrix has or we can find eigenvalues for every real matrix, which is not true. We know that there are real matrices that do not have real eigenvalue, right? So if this is true, then we can always find an upper triangle real orthogonal matrix such that Q transpose AQ upper triangular, which is not possible because there are examples. We can construct such example. Then the next question is, okay, if we cannot, using the real orthogonal matrix, we cannot upper triangularize a real matrix, then what best we can do? So can we say that, okay, if it is not upper triangular, then it is like some kind of block upper triangular? This kind of question we can ask. If it is not upper triangular, then can we say that it is upper triangular where at the diagonal we have some block, let's say one of size 1 cross 1 or 2 cross 2, this kind of thing we can ask. So we'll answer this also. This would be like a real version of Schur's lemma. But before that, let me also recall we saw some special kind of unitary matrices, which we call them as householder transformations. So they are like reflectors or rotators. So I mainly talked about real rotators and real reflectors, but there is a complex notion of rotators and reflectors also. But then that will take some changes in explaining in the explanation. But if we assume that we are or underlying field is the field of real number, then we can like construct a rotator and a rotator or a reflector, such that these matrices, these rotator and reflectors are just matrices that satisfy certain properties, like they are or real orthogonal, and they can be used to like create zeros in a given matrix or a vector. So these kind of matrices are these kind of transformations are useful in several application. One of the application is that you can like on a given matrix A, you can create zeros. If suppose A is of this form, then you can create zeros in certain certain columns using these transformation, like unitarily similarity transformation. You can create zeros using these rotators or reflectors. So one application is that they are useful in creating or they are useful in like in eigenvalue computation, because what is the main idea of computing eigenvalue uh, numerically? It's like if suppose we have a matrix A, then the idea is that you use rotator or reflector, then you convert this matrix into, it is not upper triangular, but it is like a upper Heisenberg form. What is upper Heisenberg form? That like it is almost an upper triangular matrix. It has one extra diagonal, which is a extra subdiagonal. That means below main diagonal there is one more diagonal. So it's like it is almost upper triangular. It is not upper triangular, but it is almost upper triangular, because it has like some non-zero entry in the first subdiagonal. So such matrices are called upper Heisenberg. So there is just for your information that why these rotators reflectors are useful. So you can use these rotators and reflectors to convert A into this kind of matrix, upper Heisenberg, and then there is a and then further you can use some kind of like so see this conversion you can achieve in using certain rotators and reflectors. You can always convert your matrix A into an upper Heisenberg, but from upper Heisenberg to upper triangular, that means you ultimately want to achieve this upper triangular form using similarity transformation. That means you want to find a sequence of matrices, sequence of orthogonal matrices, such that Q transpose AQ is upper triangular. This is what you want to achieve, because then eigenvalues of A are nothing but the eigenvalues of this upper triangular matrix, which are nothing but the diagonal entries. Okay, so this is achieved by so-called QR algorithm. So what is this QR algorithm? It is like um, it factorize this upper Heisenberg matrix into into QR factors. We will discuss what are the QR factors, and then from QR factors, it uses again rotators and reflectors to convert this upper Heisenberg matrix into an upper triangular matrix iteratively. Okay, and then under certain conditions, this algorithm converges. That means you can uh, always convert A into an upper triangular matrix using similarity transformation, and therefore you can identify the eigenvalues of A by looking at the diagonal entries here. So this is the basic idea of finding eigenvalues of a of a matrix using by this QR algorithm. But in the background, it is like rotators and reflectors which are useful. And I also gave you examples, or at least told you how one can create zeros, or one can choose rotators and reflectors in order to create zeros in a vector. So you can always, for a given, so what it says is that if you have a vector x, let's say Rn, And then if you choose y as this kind of vector, then you can always construct a rotator, so qw, such that qw sends x to y. So that means for any given x, you can construct this y, and you can construct this this rotator, such that it sends this to this. Okay, not this to this, but it you can create like a sequence of rotators, not only one, but like n-1 rotators, because using one rotator you can create only one zero. So in order to create zeros into these n-1 places, you need n-1 rotators. So by a sequence of n-1 rotators, you can create zeros, uh, or you can send x to y, this kind of vector. Similar thing you can do by using one reflector also. You can just choose the reflector appropriately, and then you can send this reflector also. You can construct this reflector also that sends x to y. So there is a way, and we have discussed this in the last class. So, and this also gives us a motivation to, at least in the 2 by 2 case we saw in previous class, that if we have a 2 by 2 matrix, real matrix, then we can decompose it into two factors, q and r. And that we will see that for any given matrix of any size, we can always do it in this kind. We can always decompose it into this kind of factors, and that would be called as QR factorization. Okay, this we will see in today's lecture. But let us start today's lecture um, by by giving a real version of Schur's lemma, and by looking at some applications of Schur's lemma, why this is so powerful, and why we are like emphasizing more on that. Okay, so this is the complex version of Schur's lemma. Then, as I mentioned, there is a real version. So today's lecture starts from here. So real version of Schur's lemma. Okay, so this I will give, but before that, okay, so let me state this result first. So we know that, as I mentioned earlier, that there are examples like the real rotation matrix you can take, and you can say that, okay, it doesn't have a real eigenvalues. Okay, so for such matrices, you cannot find a real orthogonal matrix that can convert this A to an upper triangular matrix under uh, real orthogonal transformation. So then the next question is what best we can achieve. So this is what is given by this Schur's lemma for real matrices. So it says that if suppose we have so I will write a parallel statement. You can see the difference between these two. So if suppose A is a real matrix of size n cross n, okay, then there exists a real orthogonal matrix. You remember what is real orthogonal? So unitary is U star U is identity when U is complex, and if U is real, then this thing would be U transpose U equal to I. If U is real, and then instead of unitary, we call it real orthogonal. Okay, so it satisfies similar condition as for unitary matrix. Okay, so then there exists a real orthogonal matrix. Let's say Q, the same size, such that this Q transpose AQ is equal to this kind of matrix. It is not upper triangular, but it is a block upper triangular matrix. So this lower part is 0, and then we have this upper triangular block, or the block, or the entries above the this block diagonal. Now this is of again size n cross n. So all these blocks are real, where k is than equal to 1, less than equal to n. So where each ai is real, is either 1 cross 1 real matrix or 2 cross 2 real matrix with a non-real pair of complex conjugate eigenvalues. Okay. So, and also moreover, these diagonal blocks, the diagonal blocks, which means this AJ may be arranged in any prescribed order. Okay, so you can see that it is parallel to what we had for complex matrices. So we have a real matrix, then instead of unitary matrix, so in here we have we know that for a complex matrix it will have n eigenvalues, so we can arrange them in some order, lambda 1 to lambda n. For real matrix we know that uh, either it will have real eigenvalue or it will have complex eigenvalue in pair. So for a real matrix, we know that if lambda is an eigenvalue, lambda is a complex eigenvalue, then lambda bar is also an eigenvalue, right? For a real matrix. So eigenvalues appear, the complex eigenvalue appear in pair, lambda, lambda bar. So what it says that instead of lambda 1 to lambda n, you can have this block a1 to ak, where either these blocks are 1 by 1 in case when this a has real eigenvalue, and or it has 2 by 2 blocks which are corresponding to complex conjugate eigenvalues. Okay, so you can arrange this similarly. Instead of lambda 1 to lambda n, you can arrange a1 to ak in any order. Then this result says that there exists a real orthogonal matrix Q such that Q transpose AQ is block upper triangular. So if all these blocks are of size 1, then it is actually the same. It's an upper triangular matrix, right? But we cannot guarantee that. So this result says that at least you can say, or what best you can say is that you can find a real orthogonal matrix Q such that Q transpose AQ is block upper triangular, where the diagonal blocks are either 1 by 1 or of size 2 by 2, where the 2 by 2 blocks are corresponding to non-real pair of complex conjugate eigenvalues. Okay, so now the proof is actually it's very similar to what we did in this case. So if you recall what we did in this case, let me recall the proof of complex case, just recalling here. So what we did, since we are given lambda 1 to lambda n eigenvalue, what I did, I chose an eigenvector x1 corresponding to lambda 1 such that norm of x1 is 1, and then I extended this basis, this x1, to a basis to an orthonormal basis of Cn, and then what I did, then I uh, constructed a matrix U1, let's say, where the columns of U1 are nothing but these, and then I did U1 star A U1, then it creates zeros in the first column. It would be lambda 1 and then 0, then we have here, and then we have a submatrix A1. Then I will do the same thing for A1 now. So this, in the next step, I will create lambda 1, lambda 2 zeros here, and then we have this row, and then we have a submatrix A2 here of size n minus 2 cross n minus 2. And if I keep on doing the same way in the same way, then after n steps, n minus 1 steps, I will get an upper triangular matrix. Okay, this was the idea. Now here in this case, we do not have eigenvalues, but what we can say that there are two cases in the real case. So I'll do similar thing. I'll just give you idea. You can do the proof yourself, or you can see the details, look into the details. I'll just give you the idea. So it is, the proof is very similar to the complex case, but here there are two cases. Either eigenvalues are real, or they appear in, or there are non-real eigenvalues which appear in like conjugate. So if lambda is an eigenvalue, then lambda bar is also an eigenvalue. So two cases. So the first case, so suppose that lambda is a real number which is an eigenvalue. If lambda is a real eigenvalue, then I will choose a real eigenvector in the same way as I did in the complex case. I will choose an eigenvector corresponding to this, and then I will extend this. So what I will do, I will find, if it is a real eigenvalue, then there would be a real eigenvector corresponding to this. Okay, so what I will do, I will find x such that norm x is 1, and then I will extend this basis to an orthonormal basis in Rn, and then I will construct an orthogonal matrix, orthogonal matrix, where the columns are nothing but x and these extra vectors, the added vectors. Now when I apply this q1 on this, then I will get 0. I will create 0 in the first column, and then we'll have a n by n matrix here, A1. Now in place of, if lambda real eigenvalue, if suppose it's a complex eigenvalue, so I'm just giving you the idea, but it follows in same way. Now if suppose lambda is a complex eigenvalue of this form, it's a non-real eigenvalue. Okay, that means beta is non-zero, the imaginary part. Then ax equal to lambda x, and suppose that x is the eigenvector corresponding to this lambda, where this x will also have this part, u plus iv kind of thing. It's a non-zero vector where u and v both are real vectors. So this x we can all write in this way, right? Now you can verify that in this case, since eigenvalues appear in pair, that means if ax equal to lambda x, then you take the bar of this, so it would be lambda bar x bar. So this lambda bar is also an eigenvalue, and you can verify that x and x bar both are linearly independent in this case. Or you can say that now you show that u and v are linearly independent. Once you have two linearly independent vectors here, what you can do, you find, you apply Gram-Schmidt on these two, and you will get w and z. You apply Gram-Schmidt on this, and then you get wz, which is a real orthogonal set. Okay, and then what you will do, now you have two vectors, two real orthogonal vectors. Now you extend these two vectors into an orthogonal matrix, orthogonal basis of Rn, orthonormal basis of Rn, and then you construct a matrix Q where the columns are nothing but these basis vectors. Now if you do this Q1 transpose A Q1 the same way, then what you will get, you will get this 2 by 2 matrix here. Then here we will have these two rows, this would be 0, and here we will have a matrix of size n minus 2 cross n minus 2, where this matrix here, 2 by 2 matrix, will be of this form, this kind of form, because this matrix will have two eigenvalues which are conjugate of each other. Okay, and then depending on the blocks, you can keep on doing the same way. You can keep on reducing A1 in the same way, and then A2, and at the end of like k steps, you will get a orthogonal matrix such that Q transpose AQ is in the given form. Okay, so this is the idea. You can explore this idea actually. So you can explore this idea. I'll leave it here, but I hope that you have understood the concept here. So you just rewrite the proof. You look at what we did in the complex case. similar idea we can use here also, and then we can prove this result also. Okay. All right.
Sir,
So yes.
sir, using householder reflectors, we can also show that A is unitarily similar to an upper Heisenberg matrix. Then also,
Right.
this theorem is proved.
You can say you can write A into an upper Heisenberg matrix, right? You can do that. So you
So,
have A, and then you will have you can apply householder transformation, and you can convert it into upper Heisenberg, right? I agree. You can do that.
sir, then this theorem will also get proved, right?
Yes.
Using this.
Yes.
Okay, sir.
Yeah, that is another way. Yes, you're right. So that is another way to look at this. So you can use householder transformation also, and then you will convert this into an upper Heisenberg form, and then this. The only problem you might face is that you just need to be careful while choosing rotators and reflectors, because in this case, this matrix A will have complex eigenvalues. So you just have to choose your these orthogonal whatever transformations you are using, rotators and reflectors, such a way that you only remain in the real arithmetic. You understand what I'm saying?
Yes, sir.
So it is because this matrix can have complex eigenvalues, but you want to find a real orthogonal matrix. So just make sure that what in the process you only choose real reflectors and rotators, so it doesn't produce any complex entry or complex arithmetic. But yes, using that idea also you can find this. So I gave this proof because it is very similar to what we did for the complex case. All right, so there are several applications of Schur's lemma. Now we can see. We'll come back to whenever we are not able to give a like in the complex case, there are many statements which we can easily state in an, or we can convert our matrix into nice form when we use complex transformations. But when we have a real matrix, and there are certain limitations. So wherever this kind of situation occurs, I will mention that whether we will look at the proof or not, but at least I will mention that there is a difference if we have a real matrix. So for example, here you can see, but then there would be several such situations. There we need to be careful when we have a real matrix and we want to use the real transformation only. Okay. So let us look at some applications of Schur's lemma. As I mentioned, one of the application I have already mentioned. It is in finding eigenvalue, eigenvectors of a matrix, which itself is a very important application. But there are several other applications of Schur's lemma. We will see in proving theoretical results also. This Schur's lemma is very useful. But there are some more applications like in proving Cayley-Hamilton theorem, or showing the other results also. Let me just mention one by one. Mm, Applications of Schur's lemma. So one first application, you can easily see that we know if A is a complex matrix of size n cross n, then there exists U unitary by Schur's lemma such that U star AU is upper triangular, where the triangular matrix has this form, where lambda 1 to lambda n are the eigenvalues of A. So clearly we can say from here that trace of a matrix, trace of A, so if I call this as T, trace of A is same as trace of U T U star. But then using the trace property, trace of this is T U star U, but U is unitary, so U star U is identity. So this is equal to trace of t, but trace of t is nothing but sum of eigenvalues. That means lambda 1 to lambda n. So what we can say is that for a given matrix A, trace of A is nothing but the sum of eigenvalues. Similarly, you can show that determinant of A is using similar way, similar argument, using the determinant property. You can say that determinant of A is nothing but the product of these eigenvalues, lambda 1 to lambda n. All right, so this is very easy to see now. Second thing is in proving Cayley-Hamilton theorem. You all know what is Cayley-Hamilton theorem. But before I prove this Cayley-Hamilton theorem, I want to make an observation here, which I will need in the proof. So let us make this observation first. So what this observation says, it says that if suppose we have two matrices, let's say the first matrix is a matrix R. It has a special form. It has zero. Let me write it in 2 by 2 block. So this zero block, which is of size k cross k, then we have some matrix here, then we have a zero matrix here. The remaining entries in the first column, they are zero, and then we have a upper triangular matrix here. So this let us call this R, and the second matrix I'm calling as T. So it also has this 2 by 2 block structure. And what is that? In 1 by 1 block, it is an upper triangular matrix. Then at 1 2 position, it has some entries, so we don't care. Here all the entries are zero, and in the 2 by 2 block, the first entry here, which is the k plus 1 diagonal entry, that is zero, but then the other entries we don't know, and this is in the upper triangular form. So if I denote entries of T as Tij, then you can say that Tk plus 1 is 0. Okay. But for the other entries we don't know, so they are in the upper triangular form. So suppose that we have two matrices R and T in this form, and now if I multiply R and T, then can you tell me what would be the, so if I write it again in 2 by 2 block, what would be the first block? Can you quickly tell me? If I multiply R and T, what would be at 1 by 1 position?
0.
At 1 position?
0.
And how about 2 1 position?
0.
0. Okay. What can we say about the next column, the k plus 1th column?
Some upper triangular matrix
Where?
in 1 2.
1 2 upper triangular? How do you know that? Just multiply. So let us multiply here. Take the, so we want k plus 1th column. Okay, so that means I have to multiply this with the column here for the first entry. What it would be?
0.
Is 0. So first entry 0. How about the second entry in this column? Second entry means second row multiplied with this k plus 1th column.
Some star means some element in there.
No, so at this position, again you see this is a k plus 1 k block here. So this for the second row also, for the second entry in this k plus 1th column here, what you will do? You will multiply the second row with the k plus 1th column here, this column. So what it would be?
Again 0.
It's again 0. And similarly, you will have k zeros here, the first k entry. What about the other entries in this column? What about the other entries in this column? Just multiply again, same way. This row here will be multiplied.
Also 0.
0. So in fact, all the entries in this column would be 0. So you see here, although here we don't know what matrix it is, if it is 0 at this position, then we can ensure that if we multiply R and T, we will create a 0. The multiplication will give us a 0 column at k plus 1th position. Okay, and for the other entries we don't know, so here we don't know what would happen. So some entries star, but this matrix again would be upper triangular. Okay, so this observation is important for us in order to prove Cayley-Hamilton theorem. So let us look at what is Cayley-Hamilton. Have you heard about this theorem before? Do you know what is this? Can you state what is Cayley-Hamilton theorem? Just tell me what you know. We will learn this again. I just want to know if you know this or not. What is
Sorry,
Cayley-Hamilton theorem?
if Px is the characteristic polynomial of a matrix of an n cross n matrix, then P of A is 0 when we replace x with A, the matrix.
Exactly. So that means every square matrix satisfies its own characteristic polynomial. Okay, so this is called Cayley-Hamilton, and this Cayley-Hamilton theorem is also very useful. We will see why this is, but before that, let me state what is that. What is the Cayley-Hamilton theorem? It says that I will write as he has mentioned. Let PAT be the characteristic polynomial of A. A is an n cross n matrix over C. By the way, here I am taking n cross n matrix over C, but if it is n cross n matrix over R, then also you can find its characteristic polynomial, and the same result is true for that also. In fact, for any given field, this result is true. If you have a matrix A where the entries are coming from a field, then you can write its characteristic polynomial, and the Cayley-Hamilton theorem is true for that also. That means every matrix satisfies its characteristic polynomial. Here, because the proof of in the complex case is much easier, so I will do it for complex case. But remember that this result is true even when the matrix is over some other field. Okay, this result is still true. Okay, so then PA of A equal to 0. That means every square matrix satisfies its characteristic polynomial. We will prove this result, but before this, you see the application of or use of Cayley-Hamilton theorem. So we'll come back to the proof, but assume that this result is true. Okay, so use of Cayley-Hamilton. So the first application of Cayley-Hamilton is that we can write. So if suppose A is a matrix, okay, n cross n matrix over C, okay, then we can write the powers of A. So like powers of A, like power AK of A as a linear combination of I A square and so on up to ak minus 1, where k is greater than equal to n. Now you can say that since we know that m n cross n over c is a it's a it's a it's a it's a vector space of dimension n square, right? So dimension of this vector space is n square. Now if I consider this set a square and so on up to ak, where k is greater than equal to n square, okay, then I can always say that if k is greater than equal to n square, then this is linearly dependent. This set is linearly dependent, and therefore I can always write ak as a linear combination of other matrices. Then what is the benefit of this Cayley-Hamilton? Because this follows because of the basis result, right? This is just because of the basis property. We can always write powers of a if k is greater than equal to n square as a linear combination of lower powers. But this result is important when we want to write ak where k is greater than equal to n but less than n square. Then we can easily write. Then we can employ this. We can exploit this Cayley-Hamilton, and we can write this. And how to do that? How to do that? So suppose that, for example, so let me show this by an example. It would be easy to understand. So suppose that we have a 2 by 2 matrix, 3 1 minus 2 0. Okay, so its characteristic polynomial is, if you look at t square minus 3t plus 2. So this is the characteristic polynomial. So by Cayley-Hamilton theorem, we can write PA of A equal to 0, right? Because of Cayley-Hamilton, because every matrix satisfies its characteristic polynomial. So this is fine. But what does it mean? This implies that a square minus 3a plus 2i equal to 0. But then this implies that a square is equal to 3a minus 2i. So now you see, I can write a square in terms of this. Now if suppose I want to write a cube, so what would be a cube? A cube would be a multiplied by a with a square. So I know a square, so a square would be 3a minus 2i. But then this is 3a square minus 2a. But then again I know a square is 3a minus 2i. So if you do the calculation, it would be 7, sorry, it's 2a, 7a minus 6i. Okay, so this is your AQ. So you can write AQ as a linear combination of I and A. Yeah. Also, if suppose the matrix is invertible, you can find the inverse using Cayley-Hamilton. In fact, you can tell whether a matrix is invertible or not by using this result. So can you characterize, can you say some condition from here, whether when we say that by looking at this polynomial, when can we say that this matrix is invertible?
Constant term is non-zero.
Yeah, constant term is non-zero, right? So if the constant term in the characteristic polynomial is non-zero, so if a constant term in this polynomial, characteristic polynomial is non-zero, then this implies A is invertible, because 0 is not an eigenvalue. That means 0 is not an eigenvalue. So that means it is invertible. Now, once we have a characteristic polynomial, we can tell immediately whether it is invertible or not by looking at the constant term. For example, in this matrix, constant term is non-zero, so this matrix is invertible. If it is invertible, then we can find the inverse. So how to find inverse? Now again look at our this equation here. Here. So what I can write from here? I can write it as a square minus 3a equal to minus 2i, right? But this can be written as a minus 3i equal to minus 2i. Now I can divide with minus 2. Then what it would be? It would be a 3 by 2 I minus a by 2 equal to I. Now clearly you can tell what is the inverse of A. It is nothing but this matrix. So now by using Cayley-Hamilton, you can find the powers of A, and you can also tell whether the matrix is invertible. If it is invertible, you can find the inverse also. Okay. Now come back to the proof. So you have already seen the use of Cayley-Hamilton. There are many other applications also, but we already know that it is useful. So let us talk about the proof. So we have to prove that every matrix satisfies its own characteristic polynomial. So proof of Cayley-Hamilton. So let's come back to the proof. Cayley-Hamilton theorem. Okay. Okay, so what is given? We are given a matrix A size n cross n, and we are also given the polynomial, the characteristic polynomial. So this is the characteristic polynomial of A. Now characteristic polynomial, since this is a matrix over C, it is a polynomial over C of degree n, right? It's a polynomial of degree n over C. Now we know that for complex polynomial of degree n over C, by fundamental theorem of algebra. Can you tell me what is the fundamental theorem of algebra? What is the fundamental theorem of algebra?
If a degree of an polynomial is n, then it can have at most n roots.
Okay, so every non-constant polynomial over C of degree n has exactly n roots. So if this is the case, you know that this PAT, this is a polynomial over C of degree n. So you can write you know that it will have n roots, but roots are nothing but the eigenvalues. We know that the roots of characteristic polynomial are nothing but the eigenvalues of A. So if suppose lambda 1 to lambda n, these are the eigenvalues, then I can write this polynomial because I know the roots. Roots are the eigenvalues. So I can write this as t minus lambda 1, t minus lambda 2, and so on up to t minus lambda n. So where this lambda 1, lambda 2, and so on up to lambda n, these are the eigenvalues of A. Okay. Now we have to show that this PAA. So what is our claim? Our claim is to show that PA equal to 0. This is what we have to show, and we are given these two things. Now what we know by Schur's lemma? So we want to prove this by using Schur's lemma. So what Schur's lemma says? It says that there exists unitary U such that U star AU is upper triangular. Okay, U star AU is upper triangular. So let me denote this upper triangular matrix as T, and the entries are of this form. Let's say lambda 1 to lambda n. So this is my matrix T. Okay. So now what I want? I want to show that this is 0. So what is this? Instead of A, I can write A as, so from here, what would be A? A would be UTU star. So I can write it as UTU star. But then what is this? So let me call this as star. So from star now, I can say what it would be. It would be, instead of t, I have to write UTU star. So it would be UTU star minus lambda 1I, then UTU star minus lambda 2I, and so on up to UTU star minus lambda Ni. Okay, but this thing I can write. So here I will write. So this thing is same as, I'll take U outside and I can write it as T minus lambda 1I, T minus lambda 2I, so on up to T minus lambda Ni U star. Can you tell me why this is true? How can I write from this to this?
So
You
we
use
can write I as U star, and then we can take
Yes,
common out of each factors.
yes, yes. So just use the property that U is unitary. Now from here, what is this? So what is the inside part? It is nothing but, if you look at carefully, it is just PA of T. Okay. Now we clearly, although we have not shown this yet, but clearly this is 0, which we are planning to show. This is 0 if and only if this is 0, right? So if we show somehow that this is 0, then from this equation we can say that PA is 0 and we are done. But this is 0. Why this is 0? So just a minute, I have very less memory battery. Just a minute. All right. So what I was saying is that if we show somehow, that PA of T equal to 0, then we are done. But why PA of T equal to 0? But PA of T equal to 0. Why this is? Because of above observation, and we are done. So this is true. PA of T equal to 0 because of above observation, the observation we made here. Here, because of this observation, this is true. Why? Because, let me write it here, why this is true. So what we are, I'm saying that PA of T equal to 0. But why this is? Because PA of T is what? It is the product of lambda 1I. So this, then T minus lambda 2I, and so on up to T minus lambda Ni. Okay. So let us look at the product of, so I will first multiply these two, and then whatever be the result, I will multiply with T minus lambda 3I and so on. So let us multiply T minus lambda 1I and T minus lambda 2I. So T minus lambda 1I is what? It is, so what would be, T is upper triangular. So T minus lambda 1I has this form. It will be 0. So the first column would be 0. Then there would be something in the first row, and then this matrix in the upper triangular form. This is my T minus lambda 1I. Okay. Then what would be T minus lambda 2I? T minus lambda 2I, it would be something here. Then this would be the first row. This column would be 0 because it is T minus lambda 2I is also in upper triangular form. Then this entry would be 0. The 2 entry would be 0. And then this matrix would be in the upper triangular form. Now you can see here, this matrix here, this is in the form of this R here, and this is in the form of this T. So when I multiply these two, what I will get? I will get the first two columns would be 0 after the multiplication, and then there would be some matrix here and an upper triangular matrix here. Sorry. Upper triangular matrix would be here. Now again, if I multiply with T minus lambda 3I, the same way, it would be again be in this form of R and T, and then after the multiplication, the third column would also be 0. And similarly, when you multiply all these factors, you will get a 0 matrix. Okay, so therefore PA of T equal to 0, and this implies that PA of A equal to 0, and this proves the Cayley-Hamilton theorem. All right, so this is fine. Okay, so we have proved two results already using Schur's lemma. Let us prove another one. Now the next result says that we have already seen some examples that not every matrix is diagonalizable, but we can say that not every matrix is diagonalizable, but every matrix is almost diagonalizable. So what I'm saying is the next is the following. So the third application we can see of Schur's lemma as follows. So I'm saying that every matrix is almost diagonalizable. So what do I mean by that? I mean that although the matrix A, it may not be diagonalizable. So the matrix A itself is not diagonalizable, but there exists a matrix B which is diagonalizable, such that norm of A minus B under a given norm is less than a given of epsilon. So what I'm saying is that this matrix A is arbitrarily close to a diagonalizable matrix, or you can say that for any given epsilon greater than 0, however small epsilon is, you can always find B which is diagonalizable, such that the norm of the difference of A and B is less than epsilon. That means B is very close to A. So for example, this norm you can choose. In fact, if you choose, let's say, if you want to see entry-wise comparison, then you can choose Frobenius norm here. You can choose infinity norm also. So whatever be the norm, you can always find a matrix B such that A minus B, norm of A minus B is less than epsilon. Okay, so it says that although it is not, the matrix is not diagonalizable, but it is arbitrarily close to a diagonalizable matrix. When I say arbitrary close, it means for any given epsilon, you can always find a diagonalizable matrix B such that norm of A minus B is less than epsilon. Okay, this is very interesting because now in theory, we know that not every matrix is diagonalizable, but in practice, because of errors, because of rounding errors, when you enter a matrix in the computer, the probability that this matrix would be invertible is almost 1. So almost every time, whenever you enter a matrix randomly, it's not like, of course, when you give particular values to A, it will be singular. But if you just randomly choose some matrix A, then the probability of A being singular is almost 0. Or you can say that the probability of A being non-singular is almost 1. Every time you generate a matrix, it would turns out to be invertible. So, or you can say that the set of invertible matrices is um, dense in the space of matrices. That means for any given matrix, you can always find for any given epsilon, if you construct a ball around epsilon around V, you can always find a matrix C which is invertible. So that means set of invertible matrices is dense in the space of matrices. So there are many equivalent this kind of statements you can you can make from this result. So what I mentioned, so I will prove this result. But using this, you can say that every matrix is almost diagonalizable. Set of invertible matrices is dense in space of matrices, and you can say the probability of a randomly generated matrix to be invertible is almost 1. Every time you generate a matrix randomly in MATLAB or in some other software, the probability of this matrix to be invertible is almost 1. Every time you'll get this. Or you can say that the singular matrices are highly sensitive in the sense that if you try to enter a singular matrix, and due to some error, if some entry of this matrix has changed, then this will become invertible. So the singular matrices are highly sensitive. So this kind of statements you can make from what I'm going to write next. So let us see. Let us write it properly now. So every matrix is almost diagonalizable. So what do I mean by that? So if we have a matrix A, then for any given epsilon, there exists a matrix B. Let me denote the entries of B as Bij and entries of A as Aij. B of the same size with n distinct eigenvalues. Now I'm not only I'm saying that every matrix is almost diagonalizable, I'm giving you more. I'm saying that you can always choose a matrix B such that this B has distinct all eigenvalues as distinct, or all eigenvalues of B are distinct with n distinct eigenvalues such that so I'm choosing this Frobenius norm, but you can choose any norm and accordingly you can construct this matrix B. For Frobenius norm, it would be easy to construct, but for other norms also it is not that difficult. So Frobenius norm of A minus B is less than epsilon. Or if you want to avoid the square root in the norm, so you can say that the square of A minus B Frobenius norm is less than epsilon. So what is this actually? You remember what is the Frobenius norm? Frobenius norm of this. So Frobenius norm of A is nothing but trace of A star square root. Take the trace of A star and take the square root, but it is again same as saying that you take the sum of squares of absolute value of each entry and then take the square root. It's the same thing. So let me write this. What is this? This is nothing but Aij minus Bij square. This is norm of A minus B. This is the Frobenius norm of A minus B square. Okay, so let us see how we can construct. So now you tell me the proof of this. I'll give you the idea, but you have to tell me how I can construct this B. This is very easy. So let's see what we can do. First, we know that A is an n cross n matrix over C. So by Schur's lemma, I will first write it in a simplified form. That means there exists U unitary such that U star AU is upper triangular. Okay. So let us denote this upper triangular matrix as the entries of this upper triangular matrix as Tij, or you can call it as T. So this is our upper triangular matrix. Okay. Now what we want, so this from here I can say A is nothing but UT U star. All right. Now what I want, so let us see first what we want. So we want a matrix B such that all eigenvalues of B are distinct, first thing. And also when I take the difference of A and B, Frobenius norm, it should be less than epsilon. All right. So what I can do, I should choose B. I can choose B as A plus some matrix, right? Plus some matrix E such that norm of E, because then it would be A minus B would be just norm of E. I should choose this E such that norm of E is less than epsilon, right? So I can choose this B as B equal to A plus E. The only thing is that this E I should choose appropriately so that all eigenvalues of B becomes distinct. All eigenvalues are distinct, and also it satisfies this norm inequality. So what I can do here, so you see here B is what? B is equal to A plus E. I don't know what is this E. I'm just giving you some idea. You tell me what I should choose. So I can write this A as UT U star. Now plus E. Now can you see this? Can you get some idea how to generate this E? Some vague idea can you give me that I should choose this E in such a way that it satisfies certain thing? First you try to find, so let me, instead of UT U star, if suppose you just have this, you just have T is the upper triangular matrix, this one, okay, this is T. This T may not have all eigenvalues distinct. So what E you can add to this T such that it has distinct eigenvalues? So first thing is, can you add some matrix E to this T such that all eigenvalues of the new matrix, let's say B, are distinct? Can you do that?
Yes, sir.
How would you do that?
Sir, add any diagonal matrix that all the diagonal entries of B become distinct.
Distinct. Yes, exactly. So if you want to see the eigenvalues of this T plus E, now we know that eigenvalues of T are the diagonal entries. So I will just choose E as he mentioned, just choose some diagonal matrix such that when you take the sum, all the diagonal entries are distinct. We can do that. So if we do this, then we can ensure that all eigenvalues of B are distinct. That is fine. But then there is another constraint. We should choose it in such a way that norm of E, Frobenius norm of E, is less than epsilon. Can we do that? So Frobenius norm, so you are saying that choose this E as diagonal matrix. So let's say alpha 1, alpha 2, and these are the diagonal entries of E. And here the diagonal entries are T11, T22, and so on, as Tnn. Now you want that Frobenius norm of E square is less than epsilon. The Frobenius norm of E square would be this. This you want to be less than epsilon. So can you find such, while choosing these diagonal entries, can you choose these alpha i's such a way that this quantity is less than epsilon? Is it possible?
Yes, sir.
You can always do that. If you can do that, then the job is done. Because then what you can do, you just write this as UT star U. So let me call this matrix as E tilde. So then your E would be U E tilde U star, because then it is just T plus E tilde U star. So eigenvalues of B are nothing but eigenvalues of T plus E star, T plus E tilde, because they are unitarily similar. But eigenvalues of T plus E tilde are nothing but the diagonal entries of these, but they are all distinct. So eigenvalues are all distinct for B. And also if you look at the norm of A minus B, it is just norm of U E tilde U star F, but the Frobenius norm is unitarily invariant. It is same as this, but this you know that you have chosen these alpha i's in such a way that this sum is less than epsilon. So you are done. Right? So now you know the proof. We can write it properly. So I will remove this idea now. So maybe I'll keep this thing here. Just for your record, this is the idea. Okay. So let me write this properly now. So I'll just write what we have explained here. So what I will do here, I will choose, let's say alpha 1, alpha 2, and so on, alpha n, such that first thing, all these tii plus alpha I, or you can say this way, t11 plus alpha 1, t11, t22 plus alpha 2, and so on, tnn plus alpha n are all distinct. So they are distinct. And second condition, you can impose that this modulus of alpha I square should be less than epsilon by n. This condition, the second condition, will ensure that the norm of E is less than epsilon. Then you can set a matrix E, which is alpha 1 to alpha n. This is diagonal. Okay, so you consider now your B as UTU star plus UEU star, which is just A plus UEU star. Now clearly this B has, the eigenvalues of B are nothing but tii plus alpha I. They are all distinct. So B has distinct eigenvalues. So clearly eigenvalues of B are tii plus alpha I. They are all distinct. And also when you take the Frobenius norm of this difference, it is just the Frobenius norm of UEU star, but then it is just the Frobenius norm of E, but it is less than epsilon by, if you take this sum of the diagonal entries of E, there are n diagonal entries, so this is equal to epsilon. So norm of B minus A f square is less than epsilon, and we are done. So every matrix is almost diagonalizable. So you can see that now we not only almost diagonalizable, we can see that we can actually find a matrix such that all its eigenvalues are distinct. So using that, we can actually say that the same proof will also work for saying that the set of or for every matrix A, we can always find an invertible matrix which is arbitrarily close to A. The same way, the same proof will work. Same way, we can say that invertible matrices are dense in the space of matrices, or you can say that the singular matrices are highly sensitive. So these kind of statements you can make from this result. Okay. So let us move back to. So I still got 15 minutes. I want to at least finish one decomposition today, which is, so we have already covered Schur decomposition. The two versions of Schur decomposition we have seen. I mentioned previously QR decomposition. So with this, I will also finish this QR decomposition. What is QR decomposition? I'll give a quick proof of it. It is very easy. So let us see what is QR decomposition. We will also see some application of this QR decomposition, but it has several applications, and it is so useful in the application that you can say it is one of the, after SVD, it is one of the most important factorization of a matrix, because it gives you a way to compute eigenvalues. It is the main idea behind the QR algorithm that computes eigenvalues of a matrix. So let us see what is QR decomposition. But before I give you QR decomposition, I want to recall Gram-Smith. So there are several ways to prove this decomposition. Because this class is on matrix analysis, so I want to give a proof that has some connection with the analysis. Okay. So, but I will give you hints for other ways also how to prove this. So let us first recall Gram-Smith process. You all know what is Gram-Smith. Gram-Smith orthogonalization process. Okay. You know what it is. So what is it? If we have a set of linearly independent vectors. So if we have a linearly independent set of vectors, let's say v1 to vn, they are linearly independent in an inner product space. It's v over the field f. So v should be inner product because then only we can talk about orthonormal. Okay. So what Gram-Smith says, it says that if we have a linearly independent set of vectors in an inner product space, then we can generate orthonormal set of vectors from this. How to do that? So that we can do in this way, in the step-by-step way. I will define u1 as v1, and then I will define q1 as u1 divided by norm of 2 norm of u1. Now when I say this norm of, so let me just write what is this norm. It is the norm induced by the inner product. Okay. Then I can do same thing for u2. So basically, in general, I can write for every j from 1 to n, I can write uj as vj minus this summation I equal to 1 to n vj qi. And once I have uj, I can construct this qj by dividing uj with its norm. Okay. Then you can check that this set q1 to qn, this is an orthonormal set. Not only that, the span of q1 to qk is equal to span of v1 to vk for all k equal to 1 to n. Okay. So this I want because with this proving QR decomposition is very easy. So this you already know. I don't have to tell much about this Gram-Smith process. Let us look at the QR decomposition. So what is QR decomposition? So with this now I will state the QR decomposition. So what is it? If we have a matrix A, so I'm first giving you for square matrices, okay? Square matrices over F. F is either R or C, okay? Then there exists Q over F, where Q is unitary when F is C, and it is real orthogonal when F is R. Okay, so unitary when F is C and real orthogonal when F is R. So for a given matrix A, there exists Q unitary or real orthogonal depending on the field, and an upper triangular matrix R of the same size. This is upper triangular such that A is equal to QR. Okay. So this result says that any n cross n matrix you can decompose into two factors. One is unitary and the other one is upper triangular. Okay. So the proof is easy again, but we'll do it in two steps. So we'll consider two cases. The first case is when A is invertible, and the second case when A is not invertible. So let us look at case 1 first. So when A is invertible. Suppose that this matrix A is invertible. So we are given only A matrix. We have to find Q and R. So A is invertible. A is an n cross n matrix. So let us suppose that A has n columns, and I'm writing the columns of A as A1, A2, and so on up to AN. So these AIs are nothing but AI is the ith column of A. So I'm writing A as column wise. Now A is invertible, A is an n-cross n matrix. So that means this A1 to AN, they are linearly independent, right? Since A is invertible, I am assuming A is invertible. This implies that the columns are linearly independent. They form an Li set. If they are Li, then I can, so Rn or Fn, depending on whether F is R or C, I can take the standard inner product and I can apply Gram-Smith with respect to the standard inner product, and I can find, so apply Gram-Smith now, Gram-Smith process to construct Q1, Q2, Q1, Q2, and so on up to Qn, an orthonormal set. This also I can do. So I was given A. So I have written A column wise. I took the column of A. They are linearly independent. I applied Gram-Smith and I found orthonormal set of vectors. Okay. Then using this QIs, I will define Q, where the columns of Q are nothing but these Q1, Q2, and so on up to Qn. Okay. So clearly this Q is unitary when F is C, because all the columns are orthonormal, and it is real orthogonal if F is R. Okay. So clearly this Q is n cross n, unitary or real orthogonal. So we have already found Q matrix. Now I need to find R. So I will define R as Q star A. So the product of Q star and A. Okay. Now can you tell me what would be, so if I denote the entries of R as, let's say, Rij, can you tell me what would be the ijth entry of R? Can you tell me what would be the ijth entry of R? So you can write this Q is Q1, Q2, Qn. So what would be this? It would be Q1 star, Q2 star, and so on up to Qn star. And you multiplied this with A, which A is A1, A2, and so on An. So you can easily see what would be the ijth entry of R. Can you tell me now what would be the ijth entry of R? So what would be this? If you multiply here, what would be the ijth entry of this product? What would be the ijth entry of this?
QI star AJ.
Yes, so it would be Qi star Aj. So Qi star Aj you can also write as, it's the inner product, right? Aj and Qi. So inner product of Aj and Qi, where this inner product is the standard inner product. Or you, if you don't want to write it in this way, you just write this. But can you tell me what would be Rij? Rij. So what would be this when I is greater than j? So if I is greater than j, what would be Rij? Remember this AK. So this Q1 to Qn, they have been formed using the Gram-Smith process, and in the Gram-Smith we know that the span of A1 to AK is same as the span of Q1 to QK, right? So from here you can say that when I is greater than j, Rij is 0. Why? Because this AK belongs to span of Q1 to Qk. And this Q1 to Qk, they are orthonormal. So this implies that Rij is 0 when I is greater than 0, but this implies that R is upper triangular. So we have R which is equal to, so this implies R equal to Q star A upper triangular, or you can say A is equal to QR because Q is unitary or real orthogonal. So when A is invertible, we can always find the two factors Q and R. Now we have case 2. So how much time do I have? So I have 4 minutes. So let's see. So case 2 is when A is singular. Okay. So let us see this. So A is singular means A has a real eigenvalue, zero eigenvalue. Okay. So let me recall what we have again. What we have seen so far, that the set of unitary matrices, or for the same reasons, set of orthogonal matrices in the space of real matrices. So set of unitary or orthogonal or real orthogonal matrices is compact. We have seen that. Okay, I have mentioned this before also. So this set is compact. And the second thing is that if minus epsilon is not in the set of eigenvalues of A, then clearly this A plus epsilon is A plus epsilon I is invertible. And this is also straightforward. If suppose minus epsilon is not an eigenvalue of A, then A plus epsilon I is invertible. Now what I am doing, I am defining AK, where what is AK? AK is A plus 1 by K I. Okay. Now one thing is clear, that so suppose this is the real line. Okay, this is 0 here. So if this 1 by K is greater than the largest negative eigenvalue, that means somewhere here. So this is the largest negative eigenvalue, and then the next eigenvalue is 0. So if this is the largest negative eigenvalue here, and if 1 by K is greater than the largest eigenvalue, that means here somewhere, then this A plus 1 by K is always invertible, right? So what I'm saying is that then this AK is invertible for all K such that minus 1 by K is greater than the largest negative eigenvalue. So if minus 1 by K is greater than the largest negative eigenvalue, then A plus 1 by K I, or you can say AK, is invertible. Okay. Now for all such K, what we can say, for all such K, we can, all such K, this AK is invertible, and from case 1 we know that for all such AK we can find a QR decomposition. So for all such K we can write AK as QK RK. This is a QR decomposition from case 1, because case 1 we have proved, so we can use it. So basically we have a sequence QK. QK is a sequence of unitary matrices in the case of complex numbers, and it's a sequence of real orthogonal matrices in case of real field. So, and we know that the space of or unitary matrices is compact. We have a sequence in this set. So this implies that This implies that there exists a subsequence convergent. There exists a convergent subsequence of this. So there exists a subsequence. You can denote it by QKM. Let's say QKM of QK such that this sequence is convergent. QKM converges to Q for some unitary matrix, for some unitary, or in case of real orthogonal matrix, when F is R, and unitary when F is C. Right? Because the set of unitary matrices is compact, so there exists a subsequence that converges. So this is fine. Now, if I look at limit of, so correspondingly, corresponding to Km, I can look at Rkm. So basically, when m tends to infinity, I can look at what is this Rkm. It is nothing but limit m tends to infinity Qkm star A Km. So first, can you tell me what is this limit here? What would be this one? As m tends to infinity, this Qkm star, this converges to Q from here. And what about this AKM? Where is this converges? Look at what is this. So this converges to A. So from here, this thing would be equal to QA, Q star A. But what about left hand side? Left hand side limit is, so when you do Q star A, let us call the left hand side limit is R. But since all these matrices here, they are upper triangular, so the limit of upper triangular matrices is again upper triangular, so R is also upper triangular. So since limit of upper triangular matrices is upper triangular, this implies R is upper triangular. So basically, you have found R and Q such that A is equal to, this implies A is equal to QR. So in any case, for a square matrix, we have found the QR factorization. Okay, we'll stop here. So if you have any doubt, you can ask. If there is any doubt, you can ask. If not, then we'll stop here and I'll see you in the next class.